In this video, we are going to tackle about the numerical methods of solving systems of linear equations using the direct methods. So this would be the first part of this discussion because this is a very long topic. So let's start with the introduction to numerical methods before proceeding with the direct methods. So numerical methods for solving systems of linear equations can be divided into two categories. First one is the direct methods, which will be discussed in this video. Is an algorithm with finite and predetermined number of steps which provides a solution. The next one would be the iterative methods, which are the methods that are useful for problems involving special and very large matrices. So for direct numerical methods, we have your Gaussian elimination and LU decomposition. So what is Gaussian elimination? It is the basic direct method for solving systems of linear equations. The bulk of the algorithm involves only the matrix A and amounts to its decomposition into a product of two matrices that have a simpler form, and this is called the LU decomposition. So this means that the matrix A can be decomposed into LU matrix, and we will go over that on the next video, but for this one we will focus on Gaussian elimination. So what are the assumptions for direct numerical methods? First one is the given matrix A is real, square, or it has a size of n by n, and non-singular. The problem AX equal to B therefore has a unique solution X for any given column vector B in R raised to n. So a square matrix is non-singular for the first assumption if and only if its determinant is non-zero. The second assumption means that we have here your matrix equation AX equal to B, wherein your A is the coefficient matrix, X is the column the column matrix for the variables, and B is the column matrix for the constants. The assumption here is that there is a unique solution for the variables for any given column vector B in Rn. In this case, the vector B or the matrix B is a vector in the real space with n number of elements. Backward substitution is used to solve linear equations when a matrix is in upper triangular form. So we will go over this using an example in the next videos or in the next parts of this video. So before we proceed, let us first define a diagonal matrix. So it is one where all elements above and below the main diagonal are 0. So if you will notice in this example, the matrix A has its diagonal. The diagonal of a square matrix, and the values or the numbers above and below these diagonals are all 0 as shown in the figure. So we can write this as Aij is equal to 0 for all. This symbol means for all, I being not equal to j. So for example, we have here this equation or example matrix. We have here a diagonal and the numbers above and below it are all 0. Why is that so? Because we satisfied this condition for it to become a diagonal matrix. Let's use the matrix here. A11, A12, A21, A22. Take note that the first number for this subscript is equal to the row number from the top. So this is row 1 and this is row 2. Hence, we have here your A1, 1, A12, and A21, A22 because this is in the first row, in the second row. And the second number there represents the column position from the left. First column and the second column. So for this one, we need to satisfy this condition for it to be called a diagonal matrix. For A12, this part, 1 is not equal to 2, or the column position and the row position is not equal. We can check if that is equal to 0. Yes, it is equal to 0. And for the term A21, 2 is also not equal to 1. The row position is not equal to the column position. And if you are going to check, it is indeed equal to 0. So for all the elements that is satisfying this condition, all their values are equal to 0. And with that, we can say that this is an example of a diagonal matrix. The matrix equation is in the form Ax equal to B, shown. So we have here matrix A, or the coefficient matrix. We also have your matrix X and matrix B, wherein X is the column matrix for the variables and B is the column matrix for the constants. So here we have your diagonal. That is an example of a diagonal of a matrix, and this is the size. Since this is a square matrix, then the position of the last element here would be naturally at the nth row and the nth column. They have the same value for the row and the column because A is a square matrix. And we have your coefficients, also n number of, or variables rather. We have here n number of variables and n number of constants. Using the diagonal matrix, the solution is obvious. Each row reads Aij xi equal to b sub I. This should be b sub I. So that if you're going to solve for the value of the variable x, that would just be equal to b sub I over Aij. Note that for the non-zero elements of the identity matrix, I is equal to j. So since this is an example of a diagonal matrix, we can also already see the solution obviously. An upper triangular matrix is one where all elements below the main diagonal are 0. So this is an example of an upper triangular matrix. This is the main diagonal, and all the elements below it are all 0. Hence, this is called an upper triangular matrix. Okay, upper triangular here. Okay, so we need to satisfy this condition for it to be called an upper triangular matrix. Using this example, for A21, 2 is greater than 1, or I is greater than j, we can check here that is also 0. It satisfied this condition. For A31, it also satisfied the condition, and also for A32. So we have here a upper triangular matrix. For the direct numerical methods, again, the matrix equation is in the form Ax equal to b in this case. So this is an example of an upper triangular matrix. Okay, so to solve this, we are going to solve backwards, or from the last row. If you will transform this in its augmented matrix, you can have this easily read. So the last row reads that ANN, this one, is equal to the variable equal to the constant at that specific position. So we can solve for it by using cross multiplication. The next row, now that we know xn, we can solve for the second row, or we can solve for xn minus 1. So if you will put it back to the linear system or the linear equation, this is the equation that we can obtain. Or you can do this by doing matrix multiplication, and that is the row by column multiplication. A multiplied by x is equal to b. So multiply this row by this column, and that would be equal to the counterpart of that row in the matrix B. So that would be using row column multiplication. This would be 0 times x1, 0 times x2, and so on and so forth until you arrive with this one, an minus 1 n minus 1 multiplied by xn minus 1. We have it here, and that would be added to an minus 1 n times xn, because that is a row by column multiplication, and that should be equal to bn minus 1. And manipulating the equation, you will arrive with xn minus 1. We have obtained the algorithm for the backward substitution using the upper triangular matrix for the coefficient matrix. So let's have an example here. We have a given system of linear equations. This can be written in matrix equation as ax equal to b, where a is the coefficient matrix, x is the column matrix for the coefficient, and b is the column matrix for the constants. And with this, we can arrive with the augmented matrix, and this will be equal to a comma b. In some books, they are using this notation, a b. This is the augmented matrix. This is equal to 1, 2, 3, 4. For the constants, negative 7. This is 0, 1, 3, 5. This is negative 12, 0, 0. This is negative 1, negative 2, 1, and here we have your augmented matrix A, B. Okay, so we can solve for the values of the variables here using back substitution. Okay, that is an augmented matrix of A and B. So let's have this example. Before that, let's define Gaussian elimination. So Gaussian elimination is the method used to transform the coefficient matrix in its upper triangular form while it is plugged in the augmented matrix of the system of linear equation. The Gaussian elimination method consists of creating the augmented matrix AB, forward elimination by applying elementary row operations, or we also call this elementary row operations, EROs, to get to an upper triangular form, and we have the back substitution to find the values of the variables. So let's have this example. Earl has 2 children, Kay and Sean. Kay is 4 years older than Sean, and the sum of their ages is 22. let K be K's age, and let S, I'll use S here, be Sean's age. Find a system of linear equation that models the facts given about the children's ages and solve for the system. How old is each child? So let us let K be equal to K's age. This is an example of an age problem in algebra, but we are going to solve it using Gaussian elimination. So the first condition is that K is 4 years older than Sean. So we can say that the age of K is 4 years more than the age of Sean. Or we can write this as S plus 4. I will call this equation 1. The second condition is that the sum of their ages is 22. So the age of K plus the age of Sean is equal to 22. Now let's try to manipulate equation 1 for us to have an easier process later on. This will be, we will transpose S to the other side of the equation. This will become equal to K minus S equal to positive 4. Call this 1. And this would be K plus S equal to 22, equation 2. Let me remove this to avoid confusion. So now we have your equations. We can do the process of the ordinary eliminations first. Let's try to do it. Ordinary elimination, that would be multiply the first equation by negative 1. This would be negative K plus S equal to negative 4, and then add that to equation 2 for us to eliminate the variable K. This would be K plus S equal to 22. If you add these two equations, you will have 0 plus 2S equal to positive 18. To get rid of the coefficient of S, let's multiply the whole equation by 1/2, and we have your value for S, or the age of Sean, and Sean is 9 years old. So have the value of S, and from here we can obtain the age of K using back substitution. Let's try to use the second equation. K plus S, but S is 9, equal to 22. We have K equal to 22, transpose 9 to the other side, that would be negative 9, and we have the age of K being 13 years old. So we have obtained it using the ordinary elimination. Now let's try to use the Gaussian elimination. To use Gaussian elimination, we need to transform it into its matrix equation first. So that would be 1, negative 1, 1, 1. Multiply this by the variable matrix, variable column matrix, and this is equal to the constant column matrix 4 and 22. So it follows the form AX B, coefficient matrix, variable matrix, and constant matrix. In its augmented form, this is equal to A comma B, or in this form The augmented matrix will look like this. 1, -1, 1, 1, 4, and 22. For this augmented matrix, we will call this row 1 and row 2. So we have here row 1 and row 2. So now that you have your row 1 and row 2 in the augmented matrix, we can use Gaussian elimination. So using Gaussian elimination method, to find the new row 2, we need to multiply row 1 by -1 or negate it and add row 2. Basically, we are using or implying the same concept for ordinary elimination, but in this case, we are only using the coefficients so that we can easily do elimination. We have here 1, 1, 22. At this, we will have the value 0, 2, and 18. If you multiply this by 1/2, you will arrive with 0, 1, and 9. This is the new row 2. So let's try to input that in your augmented matrix. We have your augmented matrix 1, -1, 4, 0, 1, and 9. Okay? So from here, we can write it in its matrix equation. 1, -1, 0, 1. That is for the coefficient matrix, multiplied by the vector or the variable matrix, and this is equal to the constant matrix. Okay, so we have it here. And with this, we can look for the last row here using row by column multiplication. We can obtain the value of S, and that would be equal to 9 years old. And to solve for the value of k, we can also again use back substitution, and we will arrive again with 13 years old. So that is how you use Gaussian elimination. Okay, so let's have another example. This is the problem. A chemist has 3 acid solutions at various concentrations. The first is 10% acid, the second is 20%, and the third is 40%. How many milliliters of each should she use to make 100 milliliters of 18% solution, if she must use 4 times as much of the 10% solution as the 40% solution? So for this problem, let us define our variables. So what I will do, I will let A be equal to the volume of the 10% acid concentration, or I will just write concentration. B is the volume of the 20% concentration or concentrated solution. C is the volume of the 40% concentration solution. All of these values will be in milliliters or ml. So we have a condition here. She should make a total of 100 ml. If the chemist is going to mix all of these three types of concentration, or all of these three types of solutions, she needs to arrive with 100 milliliters of 18% concentrated solution. So that would be the required amount, or the required volume would be 100 ml total, and its concentration would be 18%. Okay, so we also have another condition here. She must use 4 times as much of the 10% solution as the 40% solution. So those are A and C. The chemist should use 4 times as much as the solution C. So we can say that A is equal to 4 times C. Okay, now that we have your variables defined, we can now generate your system of linear equation using the conditions that was presented. So the chemist will make a total of 100 ml. So if you will add A, B, and C, the chemist should create 100 ml of solution. And using the concentrations, the solution A will have a concentration of 10%. So that would be 0.1 A. The concentration of your solution B is 20%, 0.2 B. And the concentration of your third solution is at 0.4 concentration. And this is a total of the total volume is 100, and its concentration is 0.18 or 18%. So we have your second equation. And we have your third, that will be coming from this condition, that she will use 4 times as much as C for the volume of A. So we can say that A plus 0B, if you transpose this to the other side, this will become negative 4C, and that is equal to 0. So we have established your equations, equation 1, equation 2, and equation 3. Okay, we have your equations. Let's try to convert this into its augmented matrix, and that would be looking like this. We have 1, 1, 1, 100 for the constant. This will be 0.1, 0.2, 0.4, and 100 times 0.18 is 18. 1, 0, negative 4, and 0. So let's multiply. We have here row 1, row 2, and row 3. Let's try to multiply row 2 by 10 for us to get rid of the decimals here. And we will arrive with 1, 1, 1, 100. Multiplying row 2 by 10, we will have 1, 2, 4, 180. This would be 1, 0, negative 4, and 0. And we now have your augmented matrix modified. So again, this is row 1, row 2, and row 3. Let us do Gaussian elimination. So for row 2, we will start with row 2 and then proceed with row 3 to eliminate the coefficients of the first variable. So this would be, to get row 2, remember we are doing a forward elimination here. Negate row 1 plus row 2. So that would be negative 1, negative 1, negative 1, negative 100. We have here 1, 2, 4, 180. Add these two together. We have 0, 1, 3, and 80. For row 3, we will subtract it from row 1. So we have here 1, 1, 1, 100, negative 1, 0, positive 4, and 0. So from here we have 0, 1, 5, and 100. Let's input it back or plug it back into the augmented matrix. You will have 1, 1, 1, 100, 0, 1, 3, 80, 0, 1, 5, 100. So we have your augmented matrix. Next, we need to eliminate this coefficient, the second coefficient of the third row. So we have R3. To do that, we will negate the second row and add the third row. This will be 0, negative 1, negative 3, and negative 80. And this would be 0, 1, 5, and 100. Adding these two together, we have 0, 0, positive 2, and 20. Let's try to multiply this by 1/2 to arrive with 0, 0, 1, and 10. This now will become our new row 3. And from this, we can now have your new augmented matrix 0, 1, 3, 80, 0, 0, 1, 10. So this is your new augmented matrix. Take note that this is in row echelon form. Okay? If you will recall row echelon form, this is a matrix which has the following conditions. The first non-zero number in each row reading from left to right is 1. So we call these numbers, the non-zero numbers from the left, the leading entries. So that is 1, 1, and 1. The leading entries in each row shifts to the right in the successive rows. So this is the leading entry. It shifts to the right, and then it further shifts to the right on the successive rows. The third condition is that all rows consisting entirely of zeros are at the bottom of the matrix. So this is the row echelon form. Or we can simply say this as the row echelon form matrix is the augmented matrix of the system of linear equations with its coefficient matrix in its upper triangular form and leading entries are equal to 1. Because you already know the concept of the upper triangular form, we have simplified your row echelon form. Okay, so let's try to copy your RREF, or the row echelon form, REF rather, of our computed matrix. So this is your RREF, or REF rather. This is your coefficient matrix. Notice that is in an upper triangular form. The leading entries are all equal to 1. That is in row echelon form. Okay. So what we will do here is to further do the process of elimination. Okay, so what we will do here is we will try to back substitute to solve for the values of A, B, and C, or the variables. So if you are going to back substitute, you have your equations A plus B plus C equal to 100. From the second row, that would be 0A plus B plus 3C equal to 80. And we have the last one, positive C equal to 10. So from here, we already have the value of C. C is equal to 10 ml. Doing the process of back substitution, we can obtain the values of B and C. For the value of B, we can use equation 2. This would be 80 transpose 3C to the other side. This will become negative 3C. This is 80 minus 3 times 10. And you will arrive with the value of B equal to 80 minus 30 is 50 ml. And then further doing your back substitution, we can arrive with the value of A using the first equation. That would be 100. A equal to 100 transpose B and C to the other side. That would be negative B and negative C. We have here 100 minus B being 50 and minus C, which is 10. We have arrived with your value of A. 100 minus 50 is 50 minus 10 is 40. So A is equal to 40 ml. That is how you use the Gaussian elimination to solve for the values of the variables in a system of linear equations. So now we are going to discuss the Gauss-Jordan elimination. What is this? Gauss-Jordan elimination is similar to Gaussian elimination. It starts with the Gaussian elimination method, and instead of back substitution, it further continues the process of elimination so that we will arrive with coefficient matrix becoming an identity matrix. The Gauss-Jordan elimination method consists of creating the augmented matrix AB, forward elimination by applying elementary row operations to get an upper triangular form of the coefficient matrix, and back elimination to an identity form of the coefficient matrix that yields the solution. We will demonstrate this later on using our previous example. So what is the reduced row echelon form? This is a matrix in which it satisfies the condition of the row echelon form. When we say row echelon form, remember that that is a matrix or an augmented matrix wherein the coefficient matrix in that matrix is in its upper triangular form, and the leading entries of the upper triangular form of the coefficient matrix are all equal to 1. And further, from this condition, from the conditions of the row echelon form, it also satisfies the following condition. Every number above and below each leading entry is a 0, such as in the case of this matrix. So this is the augmented matrix of a system. So notice here that we have your diagonal. The leading entries are all equal to 1. This was supposed to be a triangular matrix, but then for it to become in RREF or reduced row echelon form, it needs to satisfy this condition that every number above and below each leading entry is equal to 0. So above and below, the leading entries are all 0. So we apply the Gauss-Jordan elimination to obtain the reduced row echelon form, which immediately yields the solution of the system of linear equation. So the reduced row echelon form matrix is the augmented matrix of the system of linear equation with its coefficient matrix in its identity form. So this is the simplified definition of an RREF. So from our previous example, we have our reduced echelon form. And that is 1, 1, 1, 100, 0, 1, 3, 80, 0, 0, 1, and 10. This is the reduced echelon form of our matrix. But then, let us use or apply the Gauss-Jordan elimination for us to arrive with the RREF, which immediately yields the solution of the system of linear equation. So to do that, from here, we will use back elimination. So from our original matrix, we use the process of forward elimination. We start with eliminating the 0 of row 2, and then we proceed with row 3. And then after that, since row 2 and row 3 have already eliminated their first variable, and the remaining variables are only in the second position here or second column, then we proceeded with a forward elimination to eliminate the second variable of the third row. So that is forward elimination. Now we will use the process of back elimination to eliminate these portions in our REF matrix. And with that, if you have transformed these values, of course, in the augmented matrix, if you have transformed these values into 0 rather, then we will obtain the RREF of our matrix, immediately yielding the solution of the system. So we will start with or proceed with the back elimination. For row 2, what we are going to do is to multiply row 3 by -3 and then add row 2. Should be 2. Take note that this is row 1, row 2, and row 3. Okay. So let's continue. We have 0, 0, 1 times negative 3 is negative 3, and 10 times negative 3 is negative 30. And then copy row 2, 0, 1, 3, and 80. We will arrive with the new row 2, 0, 0 plus 1 is 1, negative 3 plus 3 is 0, and this will become equal to 50. This is our new row 2. Then, for us to eliminate or transform this into 0, we need to do back elimination for row 1. So for row 1, we will negate row 3 and add the row 1. We have 0, 0, negative 1, and negative 10. And then add your row 1. This will become 1, 1, 1, and 100. We will arrive with 0 plus 1, 1, 0 plus 1, 1, negative 1 plus 1, 0, and this will become equal to 90. We have your new row 1. If we will plug this into our matrix, we have your augmented matrix 1, 1, 1, or 0, because we have already transformed it. 0, 90. This will become 0, 1, 0, and 50. This is 0, 0, 1, and 10. If you will notice, we are getting close to our goal, which is to transform the REF into RREF. All the values above this leading entries are 0. Below this is 0. You only need to transform this value. And below this is 0. So, we only need to transform this value. And to do that, we need to transform your row 1. So, for the row 1, we will negate row 2 and then add row 1. This is 0, negative 1, 0, and negative 50. 1, 1, 0, and 90. We will add these two. 0 plus 1 is 1, negative 1 plus 1 is 0, 0 plus 0, 0, and this is 90 minus 50 or positive 40. This is our new row 1. Now if you will plug this into the new matrix or new augmented matrix, we will have 1, 0, 0, 40, 0, 1, 0, 50, 0, 0, 1, 10. So this is the augmented matrix in reduced row echelon form, RREF. So now we can now transform this into its matrix equation. This would become 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the coefficient matrix. Take note that is a diagonal matrix with the leading entries equal to 1. We have your variable matrix A, B, and C, and that is equal to the constant matrix. That would be equal to 40, 50, and 10. The matrix equation in its reduced row echelon form. This follows AX equal to B form. And if you are going to do the process of what do you call this, we will use row by column multiplication to arrive with the values. So this will become 1 times A is A, 0 times B is 0, 0 times C is 0, that is equal to 40. 0 times A is 0, 1 times B is B, 0 times C is 0, this is equal to 50. 0 times 0 times A is 0, 0 times B is 0, 1 times C is C, and that is equal to 10. So if you will notice, we already arrive with the values of A, B, and C. A here is equal to 40 milliliters, B is equal to 50 milliliters, and C is equal to 10 milliliters. Now, if you will check if we have met the conditions, the first condition is that the sum of these three solutions should be 100 ml. 40 plus 50 is 90 plus 10 is 100 ml. And there's also another condition that your A, or the solution A, should be 4 times as much as the solution C. And that is met. So we have already solved for the solution of the systems of linear equation. We can also check the concentration of the resulting solution. Your A has a concentration of 10%. That is 0.1 multiplied by 40 ml. Your B is having a concentration of 20% times 50 ml, the volume of it, plus 40% concentration for C, and that has a volume of 10 ml. So let's check whether this is equal to 100 ml with the concentration of 0.18. This is 4 plus 50 times 0.2 is equal to 10. And we have here 0.4 times 10 is equal to 4, and 100 times 0.18 is equal to 18. And 4 plus 10 plus 4 is equal to 18, and we have met the condition. That is correct. So take note again that for the systems of linear equations, we have 3 types of solution. That is the inconsistent, consistent, and the dependent solutions. Just a recall from our previous discussion. So we have learned in this video 2 things. We use Gaussian elimination to transform an augmented matrix with its coefficient matrix in its triangular form. After this, we use the box substitution to find the solution of the system. And we apply Gauss-Jordan elimination by proceeding with doing Gaussian elimination and then proceeding with back elimination and then transforming it into reduced row echelon form, and with that we can already have your solution available. And that is for this video. We will proceed with the LU decomposition for our next videos. Thank you for watching.